Welcome to the audience. First, I want to thank the organizers of this international conference for accepting my work. I'm Amina Benslim, a PhD student from Biskra University, Laboratory of Semiconducting and Metallic Materials. Our topic today is numerical simulation of indium gallium nitride Schottky solar cell. Our plan begins with introduction, then advantage versus drawbacks of the indium gallium nitride for solar cell, then modeling and simulation that consists of material parameters, software, and the device structure and simulation process. Next, we display the results and finally the conclusion. Solar cells still remain the best way yet determined to harness energy from the sun, which is the unlimited source of renewable and clean energy. Several materials were utilized to perform solar cells. The most common material used for the production of solar cells is silicon, and four group materials have been widely used for tandem solar cells for the space application. And indium gallium nitride is an alternative photovoltaic material. It has become a promising candidate for high efficiency solar cells due to its attractive features. The main drawback of indium gallium nitride is linked to its p-type doping, which is difficult to grow in good quality and one which ohmic contacts are difficult to realize. So we turn to the Schottky contact. In this work, a numerical simulation of a GaN Schottky solar cell is carried out using Silvaco Atlas simulator for selection of the suitable parameter including the indium content and the metal work function to give the best performance. InGaN is a semiconductor material made of a mix of gallium nitride and indium nitride. Therefore, its band gap range from 0.7 to 3.4 electron volt. It has exhibited a high resistance against proton irradiation damage in comparison with traditional gas and in-gap solar cell. It has good electrical and optical properties such as high mobility, high absorption coefficient, high thermal conductivity, and high temperature resistance. As for drawback, the failure to grow a p-indium gallium nitride layer because of the high residual density of donors. Therefore, the application of the ohmic contact on p-indium gallium nitride material seems difficult and lack of lattice match substrate. In this part, we are going to talk about material parameters, software and device structure, and simulation process. As we mentioned before, indium gallium nitride is a material made of a mix of gallium nitride and indium nitride, so that the electrical properties of indium gallium nitride are deduced from a linear interpolation between the value of indium nitride and gallium nitride, except for the gap, energy, and electron affinity. We must add Bowen parameters. We have used Gothi-Thomas model to calculate mobility. We have three recombination model: Shockley-Red Hall recombination, Augury combination, and radiative recombination. We used the Adachi model to calculate refractive index and absorption coefficient to calculate absorption coefficient model to calculate absorption coefficient. Modeling and simulation software and device structure. The device is simulated in the framework of drift diffusion model using the Silvaco Atlas software by applying a set of differential equations solved by the Newton-coupled and Gamma-decoupled methods. The device consists of 1.2 micrometer N-type InGaN layer and ultra-thin Schottky contacts about 0.5 nanometer is used to facilitate the transition of photons into the InGaN layer. The metal occupying 30% of the eliminated area. Firstly, we have studied various metals that are palladium, nickel, gold, and platinum. with changing the indium molar fraction from 0.1 to 0.8. And then the effect of planar work function and indium fraction in indium gallium nitride Schottky solar cell are studied. Now the results. The simulation output data is as follows. A. Short circuit current density. B. Open circuit voltage. C. Power conversion efficiency. And D. Phi factor. The results show that there is an increase in the GC and a decrease in the VOC with an increase in the indium composition. In contrast to gold and platinum, GC for palladium and nickel metals are decreasing at a certain point, and the maximum value of the conversion efficiency for each metal was as follows. From these results, we can talk about these important points. The increase in the short circuit current density with the increase of indium composition due to the decrease of the band gap. The decrease in the open circuit voltage is explained by an increase in electron affinity, and this is by a decrease in the Schottky barrier height according to the Schottky-Mott relation. The efficiency increases with the increase of indium composition, reaches a maximum value for each metal, then it decreases. Platinum metal is most suitable for developing high efficiency indium gallium nitride Schottky solar cell. This is because it has the highest value of work function. Now the effects of platinum work function and indium fraction in INGAN compound are studied. The figures show the obtained electrical output parameters of the solar cell for the different reported value of platinum work function versus indium molar fraction. The short circuit current density does change when the work function is changed, while the open circuit voltage increases with an increase in the work function. As for the conversion efficiency, it also increases with the increase in the metal work function. We can clarify an important point from the results. When the metal work function increases, Schottky barrier height increasing. According to the Schottky-Mott relation, the user is increasing the open circuit voltage. This is the reason for the increase in efficiency when increasing the work function. Finally, we have obtained the important efficiency of 22% for the optimal value indium molar fraction of 0.7 and platinum metal work function of 6.35 electron volt. In summary, indium gallium nitride Schottky solar cell was investigated using Silvaco Atlas simulator. The effect of Schottky contact materials and indium fraction in indium gallium nitride compound on the solar cell outputs were studied. The conversion efficiency reached 7.1% for platinum metal and 0.54 indium fraction. Then the effects of platinum work function and indium fraction were simulated, and a 22% efficiency is predicted for this indium gallium nitride solar cell design when platinum work function reached 6.35 electron volt with 0.7 indium fraction in indium gallium nitride component. Thank you for your attention.